Hello everyone. In this video, I'm going to go over some homework on normal p-values. So I've pasted in a couple of boxes here from our notes. So for all of these questions, you're going to find the appropriate p-value and draw a picture. Oh no, that means you have to see my thumb drawings. And draw a picture of the distribution of the sample means with the appropriate tails shaded and the z-scores and areas labeled. Okay, so I pasted in this formula for the z-score of a sample mean of size n from a population with mean mu and standard deviation sigma. And then down here is the instructions on how to find actual p-values. So there's left-tailed p-values, right-tailed p-values, and two-tailed p-values, which correspond to the areas that you're taking under the bell curve. All right, so let's go ahead and get into it. The recommended dietary allowance, RDA, of iron for American women aged 18 to 50 is 18 milligrams per day. A random sample of 45 American women aged 18 to 50 found a sample mean of 16.68 milligrams per day. Okay, so this is a little bit lower than the recommendation of 18. So assuming that the mean intake for American women aged 18 to 50 is the same as the RDA, and the standard deviation of intakes is 4.2 milligrams. So now we have three questions. What is the probability of finding a sample mean as low as or even lower than 16.68? What is the probability of finding a sample mean as high as or even higher than 16.68? And then lastly, what is the probability of finding a sample mean as far from the population mean or even farther than 16.68? So for all three of these questions, we need to first find the z-score of this sample mean of 16.68. So I'm just going to do a little bit of drawing on here and label my variables, and then let's calculate the z-score. Okay, so here I have my pen, and let's see. So when are we told any of the actual variables? Okay, so this is the sample size, so this is n. What else? That's ages. Sample mean is here. So this is our m. My beautiful mouse drawing, sorry about it. And then what else? Assume that the mean intake for American women aged 18 to 50. So here, the mean intake for American women, this means the population mean. So here they're telling us what is the population mean mu, and they're saying assume that it's the same as the RDA, the recommended dietary allowance, which is given in this first sentence back here. So you have to do a little bit of trawling around to find that this number is what we're supposed to actually use for mu. Wow, that might be the worst mu I've ever drawn. Sorry. Okay, and then we're also told assume that the standard deviation of intakes, I assume they still mean for American women, like all American women, is here. Okay, so this is our sigma. All right, so we have all four variables that we need to calculate z, and I'm going to just copy paste the formula and do that. So here's our handy dandy z formula. It has four numbers that go into it, so you have to be pretty careful about putting them into the right places. That's what students usually end up messing up. Let me unbox this. Yeah, an unboxing video. You thought it would be exciting and I would unwrap a present, but it was an equation. Okay, so m, our sample mean is 16.68 minus population mean, which we were told to assume is 18. And then on the bottom of the fraction, we have another fraction, fraction under fraction, a stack of fractions. How exciting. We were told to assume standard deviation is 4.2, and we divide that by the square root of the sample size, which is 45. Okay, so I usually see that students, if they're using a 4-function calculator, they mess up this part because of the double fractions, and they kind of screw up the order of operations a lot of times. I've tried to give you guys some advice in class about how to do this correctly. But one way to definitely avoid doing mistakes is just replace one little thing at a time. So you could do the subtraction, it's 18, negative 1.32. So do that one little subtraction there. And then the next part on the bottom I'd probably do is the square root of 45. See what that is. This is like a good advertisement to buy a scientific calculator, honestly. It's just easier. 6.71 if you can afford it. Okay, and then I would do the division in the bottom part here, and then I would do the big division. I should be using approximate symbols here instead of equality, but whatever. Okay, 4.2 divided by 6.71. So on the bottom, I'm just going to round it through 2 places, I guess, 0.63. 0.63. My negative went in front instead of on the top. It's the same thing, but let me just put it on top so you guys see I'm not making weird changes. And then finally I would do negative 1.32 divided by 0.63. Okay, and then that should come out negative. Negative 2. If I round this to 2 decimal places, I have to round up the 5, so that's going to go from 09 to 10. So 2.10, and that should be negative. Okay, now let's see what I would get if I plug this whole thing into like a scientific calculator that I have parentheses on. So I actually do have parentheses on this little Microsoft calculator here. So if I was going to do it with parentheses, I would do 16.68 minus 18, close parentheses, divide. Now I need more parentheses on the bottom. 4.2 divide by, you see where I'm typing up here. And then I would put parentheses around the square root only because this little Microsoft calculator, you have to press the number and then the square root. So I don't want to get the square root of the whole bottom, just the 45 part. Okay. Close parentheses, hit enter. Yeah, so I'm getting the same thing, but now you see it actually rounds to negative 2.11. So like I'm off by 100th of a place because of these intermediate rounding steps that I did. It's not a huge deal, but just like the more you round on little steps, the farther away your answer is from the real answer. I'm a mathematician, so I find that interesting. Okay, right, let's just go with this for our z-score. This is close enough. Now that I have the z-score, I want to know these probabilities. So I'm looking at this instructions here for the different p-values. I have left-tailed, right-tailed, two-tailed. So left-tailed p-value is the probability that a randomly selected sample mean would be as low as or lower. Why is that a left tail area? Because that's where the z-scores are that are as low as or lower than your z-score. They are to the left of that z-score. The z picture is on the z is on the horizontal axis. The lower values are to the left. If you want to know the probability of getting a z-score or a data value as high as or higher than your sample mean, that is a right-tailed p-value because the z-scores to the right of your z-score are higher. And then if you want to know the probability of getting a sample mean or a z-score as far as or farther from the mean than yours, then you're doing two tails, and each of those two tails should be placed symmetrically as far away from the mean as your z-score is far from the mean. Whether your z-score was positive or negative, they should be placed the same distance. So the one on the left will use the negative version of your z-score, and the tail on the right will use the positive version of your z-score. But you only need to calculate one of those two tails, and then you can just double it because of symmetry. The left and the right tails will have the same area. Okay, I hope that made sense. I'll draw a picture to make it make more sense. Okay, so let's draw a picture. My beautiful mouse drawings. Here we go. Let's see if I can do it with a mouse. Whee! If I can't, then I'll do it with my thumb, which might be even worse. Okay, well this isn't very symmetrical. I should have made this one longer, I guess. Okay, so the mean is in the middle here, which is z equals 0. Z-score for the mean is always 0. Okay, and then our z is negative 2.10, which is like over here somewhere. So this is, I'm sort of running over the next problem. Negative 2.10. Oh my gosh. Oh, I did it. All right, and then we are looking for the probability sample mean as low as or lower. So as low as or lower sample means would have z-scores over here, lower than this one. So it's a left tail, so we want to know what is this area in this left tail. So we're going to use our table of areas and look up the CDF, otherwise known as the area to the left of this z-score of negative 2.10. Okay, so let's get our little table out. And here it is. And so let's see, I'm going to get my highlighter. On the negative side, I'm looking for z of negative 2.10, so negative 2.10, I think it should be this one right here. The area of 0.0179, 0.0179, 0.0179. Okay, so I did my drawing with the area labeled and the z-scores labeled, and now I should actually like type this answer in a normal way over here, I think. So probability is p equals 0.0179 or 1.79%. By the way, I'm calling this p because this is a p-value. See this table up here? This is p-values. So you can call these areas that you get little p, and that is called a p-value. All right, so now if we want to do the next question, what is the probability of finding a sample mean as high or higher than 16.68? So that's going to be the right tail, except it's not just the tail, it's like the butt too, right? Like this whole hump here, and then also the tail. So in other words, for the second question here, we want this area over here, like all of this. This is for z-scores that are larger than our z-score of negative 2.10. So how do I get that area? Making it kind of a terrible mess here, but that's this area. So I get that by just doing 1 minus 0.0179, 0.0179. All right, and then I can put that into a calculator, and I get, what do I get? 9821, 9821, 9821, or 98.21%. Okay. So the probability of getting a sample mean as low as or lower than 16.68 was very small. And then the opposite probability, getting one as high as or higher than that, is very large. And then we can lastly do this question of what is the probability of finding a sample mean as far from the population mean or even farther. So let me draw you a picture to explain this. Maybe I'll just pause while I draw. Okay, so here is basically the picture that we have. This is my very rough thumb drawing, sorry about it. So this is negative 2.10. This is our z-score for our sample mean over here. Now I want to know the probability of finding a sample mean with a z-score as low as this as far as this or farther from the population mean. So as far or farther, look at how far this one is from the mean. How far away is that from the mean? Where are the z-values that would be farther than that? Aren't all these ones over here going to be farther? Yeah, so I want the probability of getting any of these z-scores over here, but there's also ones that are over here that are as far or farther than my z-score of negative 2.10. If I just come over here as far to the right as I was to the left, which would be right at 2.10 positive, then these scores are also as far or farther. Oh my gosh, I'm so bad at this. Sorry, I just like immediately went out of bounds. These z-scores over here are also as far or farther from the population mean as the ones that I've shaded over there on the left. I really hope you guys can understand these terrible drawings. I'm sorry I'm so bad at drawing. At least you guys see that it doesn't actually matter if you have much skill or not. Okay, so this is a two-tailed p-value. So we already know what the area of this left tail is, right? We looked it up. Up here it was 0.0179. Okay, so what is the area of this right tail over here? It's also 0.0179. Because it's symmetrically placed, they should be the exact same size and shape. Okay, so the answer for what is the probability of this and what is that total area is, it's just 2 times the left tail. So 0.0179, whatever that turns out to be in the calculator. 0.0358. So 3.58% probability of getting a sample mean as far or farther from the population mean as the one that we had, which was 16.68. Okay, so that is it for this question, and guess what? They're all pretty much like this, except in some other ones your z-score might turn out to be positive instead of negative. That's really the only different thing that could happen. So let's look at the next one, and I think maybe that one's not like that because this sample mean is less than the population mean again. I believe the last one, yeah, the last one has a sample mean that is above the population mean. So you could skip to that question if you want to see the other way of doing these problems, but I will do the second part here first. So a study by researchers at the University of Maryland addressed the question of whether the mean body temperature of healthy adults is really 98.6 degrees Fahrenheit. The researchers found that a random sample of 35 healthy adults had a sample mean of 98.3 degrees Fahrenheit. Suppose that the mean body temperature of healthy adults is really 98.6 with a standard deviation of 0.63 degrees. I know I already used this question, I think, in class with a different sample size, so I've just adapted it to do different things in different assignments. You can always resample from a smaller subset of a sample to get another problem. Okay, so what is the probability of, we're looking at as far or farther first, then as low or lower, and then as high or higher. So we're going to do the two-tailed one first with as far or farther. But before we do that, we need the z-score, and to do the z-score, we need these 4 values. So let's go ahead and do that. So you need to identify which of these numbers in the problem are what. Let's see, so researchers found a random sample of 35 healthy adults, so 35 is n, sample size, had a sample mean, so this is the sample mean, m. Suppose the mean body temperature of healthy adults, here healthy adults means all healthy adults. Suppose that that mean is really this, so that's our population mean. And then with a standard deviation of 0.63, so this is our sigma. Okay, so now we have all the values, we can plug them into the z formula. Okay, so this is what it looks like when I plug them in. And now I'm going to put this into a calculator, and I'm going to round it to 2 places like I always do my z-scores. So I'm getting negative 2.82. Right, that's a pretty small z-score, but pretty far out there. Okay, what is the probability of finding a sample mean as far or even farther from the population mean than this? So sample means further from the population mean than this would either have z-scores that are less than this one, or on the positive side, they would have z-scores starting at 2.82 positive and then up from there. So let me draw you a picture illustrating that. Okay, here is my beautiful thumb drawing, a little better than usual. And so now if I want to find the area of these 2 tails together, I'm going to look up the area of the left one using my table of areas under the standard normal curve. I always look up the area of the left one using the negative version of the z-score because that's what the table has in it, right? It has left areas. So we're going to go here, negative 2.8, what was it? Negative 2.82, which will be 0.12, this 0.024. Okay, so this is going to be 0.0024, and then that is also going to be the same area over here because of symmetry, 0.24. Okay, so the total area together should be 2 times 0.024. And let's go ahead and just type the answer here. 0.024, which I think should be 0.048. 24 times 2, 0.48% probability. So very small probability of getting a sample mean as far as or farther from the mean than this one, which basically suggests that, like, well, if the real mean of all healthy adults is 98.6, it would be really weird to take a random sample of 35 healthy adults and get a sample mean of 98.3. So maybe 98.6 might not be the real population mean, is kind of what this suggests. but we'll talk more about that in a future class. Okay, so now we can easily answer the next one. What is the probability of finding a sample mean as low as or even lower than this? I think I can just kind of point to like the left tail here. That's what we're looking at. This left tail area is the probability of getting a sample mean as low as or even lower than this. So that would be P equals 0.0024 or 0.24%. And then the as high as or even higher than this question, I guess I could kind of use my picture again. It's maybe a bit sloppy to keep reusing the same picture, but for the right tail, we're looking at a huge right tail of like starting from here and going all the way over here, including this green part. So all of that area that I have in orange there, which would be P equals 1 minus 0.0024, which I suppose is 99.76% probability of getting a sample mean as high as 98.3 or even higher. Okay, last question. The Educational Resource Service publishes information about wages and salaries in the American public school system. According to ERS, the mean annual salary, this question is from a few years ago, but I'm not sure what the salary is up to now. I think this question is maybe as old as like 15 years. Sorry about that. According to the ERS, the mean annual salary is $49,000 with a standard deviation of 9.2 thousand. So the fact that they've written these thousands in words, I think means they kind of want us to use that as like a unit and then use these like just 49 and 9.2 as the variables in this question. But you could write it out as like 49,000 and use that number as long as you're consistent. Okay, anyway, a random sample of 90 teachers found a sample mean of 49.3 thousand. So let's go ahead and identify our variables here. So mean annual salary, this should be our population mean. So this is mu. Standard deviation of 9.2, that's going to be our sigma. Random sample of 90, that is our n. And then sample mean, this is our m. Okay, so now we can go ahead and calculate z. So here is the formula, and now I just need to fill in the pieces. So m is 49.3. I'm going to do it without the 000s, just treating the thousands like units, as if it was like 49.3 oranges or 49.3 miles or something. Okay, so 49.3 minus population mean of 49.0. So I already see I'm going to get a positive z-score. It's going to be to the right of the middle. And then on the bottom here, let's see, 9.2 slash square root of 90. Okay, so now I throw this in a calculator. Hopefully I do this part right. Okay, so I got 0.31. All right, so what is the probability that the sample mean would be this high or even higher? So that's a right tail. This low or even lower, that's a left tail. This far or even farther, that is a two tail. So let's just go through all three of these. Gonna pause it and do another beautiful thumb drawing. Okay, so I've illustrated the right tail here. And how do I get the area of this right tail? I'm gonna do 1 minus the table value, the CDF cumulative distribution function for this z-score. So I need to look up 0.31 in my z-score table. Positive side, 0.31, getting 0.6217. 6217. 7. Okay, so that is number 7. And then for the second one, as low or even lower, I'm looking at, that is going to be the, I'll just be a little bit lazy and draw on my original picture again. So that is going to be this white area here. or now it's yellow, I guess. Okay, so how do I get that area? That actually, oh, I'm sorry, I forgot to do the 1 minus part in the last question, so that actually was the wrong answer right here. 0.6217 was what I should have subtracted from 1. So this should have been 1 minus 0.6217, which would be 3783. Pardon my arithmetic, which means that down here we would have, this would have been 0.6217 down here. And it's a good thing I'm almost done because I have to go to class in a minute. Okay, so last question is, what is the probability that the sample mean would be this high, or sorry, this far or even farther from the population mean? So let me draw you a picture for this for the two tails. Okay, so one of my tails is over here on the right, and my other tail would be over here on the left, symmetrically placed. So negative 0.31. So if I was starting the problem with this picture, then it would be easier for me to look up this area right here in the table, look up negative 0.31, negative 0.31, 3783, 3783. But at this point in the problem, I actually already knew what the right tail was, which was, well, the same thing, 0.3783. So if you already had this kind of like prior knowledge of what the right tail was, you could just double that to get both tails. If you started with the two tails like this, then it would be easier to look up your negative z-score, get the left tail, and then double that to get both tails. Either way, you should get the same answer, which is 2 times 0.3783. Throw that in a calculator. You get 0.7566 or 75.66% probability. And that is it for this homework. Hope it made sense. If it didn't, come to office hours, send me an email, and I'll see you in class.